Hello everyone. In the last lecture, we were discussing about Ro-vibrational transitions. Ro-vibrational transitions. Ro-vibrational stands for rotational plus vibrational. So, this is rotational plus vibrational. In other words, if we vibrationally excite a molecule, it is also rotationally excited or de-excited. In today's lecture, first we will revisit the Born-Oppenheimer approximation. So, first we will talk about Born-Oppenheimer approximation. This approximation separates electronic motions from nuclear motions, or in other words, this is a way of separating electronic energy from the rotational and the vibrational energies. Let us try to imagine what happens to the electron when we stretch a bond in a molecule. Do they stay where they originally were, or do they move? Because of the difference in the energies and the difference in the masses of the electrons and the nuclei, what happens is that the electrons change instantaneously compared to the speed with which the nuclei are moving. It enables us to discuss vibration and rotation independently of the electrons themselves. So, we can just consider the molecule rotating and vibrating in the potential energy well. We can assume that the potential energy or the potential energy well does not adjust because of the vibrations and the rotations. So, this is an incredibly good approximation. Moreover, due to the differences in energies, we can largely separate the vibrational energy from the rotational energy and just consider the total rho vibrational energy, that is, we will write E total. So, this total rho vibrational energy is the sum of the vibrational energy and the rotational energy. So, we can write E total equals E rotation plus E vibration. So, let us now consider vibration and rotation to be independent. We will also ignore the centrifugal distortion for now. The energy of a molecule, that is in the V vibrational state and the J rotational state, is just the vibrational energy plus the rotational energy. So, we can write nu bar in wave numbers when the vibrational state is V and the rotational state is J equals nu bar V plus nu bar J. So, nu bar V we can write V plus half nu bar E minus V plus half whole squared nu bar E chi E, and the rotational energy we can write B times J plus 1. So, we are considering an harmonic rigid rotor or an harmonic diatomic molecule which behaves like a rigid rotor. So, the first two terms here comes from the vibrational energy, and the last term comes from the rotational energy. To predict the spectrum that will result from the Ro-vibrational transition, we need to take into account of the selection rules. So, the selection rule for an anharmonic oscillator is given by delta V equals plus minus 1, plus minus 2 and so on. And for a rotational transition, for a rigid rotor, the selection rule is given by delta J equals plus minus 1. So, delta nu greater than plus minus 1 will exhibit much weaker intensities. So, let us see how these selection rules affect the spectrum. Let us look into the Ro-vibrational energy levels again. So, these are the expanded form of the Ro-vibrational energy levels, and we will focus only on the fundamental band in which we excite molecules from V equals 0 to V equals 1. So, the delta J has to be equal to plus or minus 1. So, what does this mean? This means I can get transitions where delta J equals plus 1. That means, I can get transitions from V equals 0, J equals 0 to V equals 1, J equals 1. I can get transitions from J equals 1 to J equals 2, also from J equals 2 to J equals 3 and from J equals 3 to J equals 4. Similarly, I can also have transitions where delta J equals minus 1. So, in this case, we will have transitions from J equals 1 to J equals 0, then J equals 2 to J equals 1, J equals 3 to J equals 2 and from J equals 4 to J equals 3. So, in the blue transitions, J is increased by 1 and in the red transitions as shown in the figure, J is decreased by 1. So, when J is increased by 1, we identify these transitions as the R branch. All these R branch transitions will be greater than the fundamental frequency. The fundamental frequency can be identified in a hypothetical transition in which delta J equals 0 or in other words in which J does not change. When J is decreased by 1, we identify these transitions as P branch transitions. These transitions where J has decreased will be at a frequency smaller than the fundamental frequency. So, we use our knowledge of the vibrational and rotational energies and the selection rules to predict transitions in the P branch where J decreases by 1 and in the R branch where J increases by 1. So, for the P branch, the J value changes from J double prime to J prime. So, this double prime indicates the initial state and the J single prime or this J prime indicates the final state. So, this is purely a convention and we have discussed it before when we were discussing rotational spectroscopy. So, for the P branch we can write J prime, that is the final state, equals J double prime, that is the initial state, minus 1. So, this is for the p branch, or from here we can write j double prime equals j prime plus 1. So, we can write this nu bar equals nu bar 1 plus b times j prime plus 1. So, this is the energy of the V equals 1 state, and we have to subtract nu bar 0 plus b j double prime times j double prime plus 1. So, this is for V equals 0. So, now if we put this j prime equals j double prime minus 1, or in other words if we put j double prime equals j prime plus 1, what we get is nu bar equals nu bar E minus 2 nu bar E chi E plus b j prime times j prime plus 1. Then we have minus b j prime plus 1 times j prime plus 2. So, this part nu bar E minus 2 nu bar E chi E comes from this nu bar 1 minus nu bar 0, considering an anharmonic oscillator. So, if we further simplify this, what we get is nu bar E minus 2 nu bar E chi E minus, if I take b and j prime plus 1 common, then we have minus j plus 2. So, this j cancels out. So, we have nu bar E minus 2 nu bar E chi E minus b or 2 b j prime plus 1. So, this is for the p branch. So, we will consider r branch now. So, for r branch I can write j prime equals j double prime plus 1. So, similarly we can write nu bar equals nu 1 bar plus b j prime times j prime plus 1, then minus nu bar 0 minus b j double prime times j double prime plus 1. So, now if we put this condition, that is j prime equals j double prime plus 1, and we simplify this expression, what we get is nu bar equals nu bar E minus 2 nu bar E chi E plus 2 b j double prime plus 1. So, there are two differences between p and r branches. Number 1, in the p branch, the difference between the rotational energies is negative. In other words, we have a negative sign here. However, in the r branch, it is positive because we have a positive sign here. And number 2, in the p branch, we define the energy difference in terms of j prime, the final j value, but in the r branch we define the energy difference in terms of J double prime. So, this is solely done to show the similarity between the expressions. Note that we never get a transition at exactly the fundamental frequency. So, these two equations, one is this one and the other is this one. So, these two equations define all the spectral lines in the P branch and in the R branch. There are no other branches for diatomic molecule. For the P branch, the minimum value of J prime is 0. The first line of the P branch will be at nu bar E minus 2 nu bar E chi E minus 2b. The minimum value of J double prime is 0 as well. So, the first line of this R branch will be at, so the first line will be at nu bar E minus 2 nu bar E chi E plus 2b. So, there will be a gap of 2b and 2b, that is a gap of 4b between the first line of the P branch and the first line of the R branch, and in the middle of that two lines will be the gap for the fundamental frequency. So, this enables us to identify what the first line in the P branch is and what the first line in the R branch is, because all we need to do is to find that gap. Once the gap is found, the lines at smaller frequencies are P branch lines and the lines at higher frequencies are R branch lines. The center of this gap associated to the fundamental frequency is known as the band origin or the band center. So, there will be two sets of rotational fine structures on either side of this band origin, and this is exactly what we saw in the last lecture for the carbon monoxide spectrum. This is a Ro-vibrational spectrum provided by our expression for the spectral line frequencies for transitions in the P branch and the R branch. So, this is the P branch and this is the R branch. The shaded part shown here shows the gap at the fundamental frequency. The R 0 is the first line in the R branch, as it is associated with j equals 0 to j equals 1 transition. So, j equals 0 to j equals 1. So, j equals 0 is for v equals 0 and j equals 1 is for v equals 1. The first line in the P branch can be labeled as P 1, because it is associated with j equals 1 to j equals 0 transition. Again, here j equals 1 corresponds to v equals 0 and j equals 0 corresponds to v equals 1. So, the number this R 0 or P 1, this number refers to the initial level, because in this case the initial level is 0 and in the other case the initial level is 1. This is just a convention. The numbers that we generally use when we label a spectral line refers to the initial state. In this analysis, where we have ignored the centrifugal distortion, the spectral lines are evenly spaced. The distance between any two spectral line ignoring the gap at the band origin is 2b. So, we can write this as 2b. So, this explains the carbon monoxide spectra. In the low resolution spectra, the low resolution of the spectrometer averages out the fine rotational structures, and so we have two broad bands. We have the p band and the r band, and we have two broad bands associated with this unresolved p and r spectral lines. But at high resolution, we have a different spectrum. So, at high resolution, we can see the rotational fine structure, and that these are evenly spaced lines. So, in the next lecture, we will continue our discussion on the vibrating diatomic rotor. So, we will end this lecture by solving a problem. So, we have the problem here. The equilibrium bond length and the force constant of LIF are given. So, the question is, using rigid rotor harmonic oscillator approximation, estimate the energies of the first three rotational levels in the V equals 0 and V equals 1 vibrational states. The atomic weights of lithium and fluorine are given. Also, there is a question, what are the frequencies of the first lines in the R and P branches of the Ro-vibrational spectrum. So, because we are only considering rigid rotor harmonic oscillator, so then the energy E as a function of V and J can be written as E vibrational plus E rotational. So, we can write this as V plus half nu bar, because we are only considering the harmonic oscillator, plus B times J times J plus 1, because we are considering rigid rotor. So, in order to find the energies, we have to find nu bar, also we need to find B. So, first let us find B. So, we know B equals h by 8 pi squared I c. That means, we need to know the value of I, and also we know I equals mu, that is reduced mass, times R equilibrium squared. So, in order to know I, that is the moment of inertia, we need to know the reduced mass. So, let us start from the beginning. Let us try to find the reduced mass. So, the reduced mass is given by the atomic weights are given. So, 6.015 times 18.998 divided by 6.015 plus 18.998. So, this is in AMU. So, the answer is 4.569 AMU. Now, once we have found out the reduced mass, let us look into the moment of inertia I. So, I equals mu times R equilibrium squared. So, that is the value of mu is 4.569 AMU, and we convert that into kg. So, we have to multiply with 1.661 times 10 to the power minus 27 kilogram AMU inverse, and then we have to multiply this with the R equilibrium squared. So, R equilibrium is 156 picometer. So, we can write 156 times 10 to the power minus 12 meters whole squared. And once we do this calculation, what we get is 1.846 times 10 to the power minus 46 kilogram meter squared. So, now we can find the value of B. So, the value of B is given by h by 8 pi squared I c. So, let us put the values. The value of h is 6.626 times 10 to the power minus 34 joule second. Then I have 8 times pi squared. Then I have moment of inertia, that is 1.846 times 10 to the power minus 46 kilogram meter squared, and then I have the speed of light c, that is 3 times 10 to the power 8 meter per second. So, if we do this, the answer we get is 151.6 meter inverse. So, we can write this as 1.516 centimeter inverse. So, now we have found out the value of B, which was needed for this energy expression. So, now we need to find the value of nu bar. So, nu bar is given by 1 by 2 pi c root over k by mu. So, let us put in the values. So, 1 by 2 pi times 3 times 10 to the power 10 centimeter per second, and then we have k, that is 250 Newton meter inverse. So, this is given here, divided by mu, that is 4.569 a mu times 1.661 times 10 to the power minus 27 kilogram a mu inverse. So, this whole thing in the bracket to the power half, and this gives the answer as 963.7 centimeter inverse or wave numbers. So, now we have found the reduced mass, we have found the moment of inertia, and we have also calculated the harmonic frequency. So, the energy for the rotational levels for vibrational level equals 0 is given by E 0 comma j, that can be written as 481.9, because V equals 0. So, we have found out nu bar. So, all we are putting here, this is nu bar by 2 plus 1.516, that is the value of B j times j plus 1. So, this is the general expression for any j level, and E 0 E 1 j is given by 1445. So, this is equivalent to V equals 1 plus half nu bar plus 1.516 j times j plus 1. So, we have to find the energies of the first 3 rotational levels for V equals 0 and V equals 1. So, I will not do the entire calculation, but I will just try to make a table, so that you can do the calculation and check it yourself. So, we will put j here. So, j is 0, 1, 2, these are the first 3 j levels. So, here we will put E 0 j in centimeter inverse. That means, this is for V equals 0, and I will put in another column E 1 j in centimeter inverse, that is for V equals 1. So, if you do the calculation with this expression, this energy expression, you get the energy as 481.9, because here j equals 0. If you put j equals 1, you get 484.9. So, you see the energy increases, and for j equals 2, V equals 0, the energy is 490.9. Similarly, for the V equals 1 state, j equals 0, the energy is 1445, that is this number, because j equals 0. For j equals 1, it is 1448, and for j equals 2, it is 1454. So, now we also need to find the first lines in the P and the R branches. So, for the first lines, let us say I want to find the first line in the P branch. As we have discussed in the lecture, this is given by nu bar minus 2 b. So, this is 963.7 minus 2 times 1.156, everything is in wave numbers. So, the answer is 960.7 wave numbers. Now, for the R branch, that is nu bar R is given by nu bar plus 2 b. So, now the answer will be 963.7 plus 2 times 1.156 wave numbers, and so this will be 966.7 wave numbers. So, here we have solved the entire problem, and in the next couple of lectures, my co-instructor Anirban Hazra will talk about the selection rules and the wave functions related to vibrational spectroscopy.